You're set to go.
Okay. This should be fun. Good evening, everybody. Thank you very much for joining. I'm not going to attempt to speak to you in Hebrew because that would be a disaster. But thank you nevertheless. So, my name is, well, let's see, does my Australian or American accent work better? My name is Mark Mandel, or Mark Mandel, depending on whichever works better for you. I'm a developer advocate for Google Cloud Platform, which means I get paid to come out and do fun things like this. Come visit you all here in Tel Aviv and tell you interesting and fun stories about fun and interesting technologies. Before we continue, a little bit of self-narcissism. Who here listens to the Google Cloud Platform podcast? 4 people in the front. That's fine. If you're at all interested in any of this stuff, and there'll be several links to this throughout the talk, I am one half of the Google Cloud Platform podcast as well. We like to talk about all sorts of fun things, including the stuff that we're talking about today. So if this interests and excites you in any way, shape, or form, hopefully you can find some more content. I've got my Twitter handle there as well. It's neurotic, which is something that is a throwback to when I was 15. And my card's up the front here, so if you don't get the chance to ask me questions this evening, please take my details down. Feel free to harass me at any given point in time. It is technically my job. Okay, you can all hear me okay?
Yeah.
Good. All right, let's get going. Okay, so we're here to talk about scalable real-time microservices with Kubernetes and gRPC, because that's about as buzzwordy as we could possibly get. We could probably throw some other stuff into it.
IoT, big data.
Yeah, sometimes I actually pitch this as an IoT talk. It's fun. So, what on earth are we actually even talking about today? From the title of the talk, you probably think that we're probably talking about, well, Kubernetes and gRPC, probably Docker, and all that sort of fun stuff. But rather than specifically talking about these 3 things, what I actually really want to talk to you about is this. Now, this has been an interesting one because culturally, I know there are some people who have no idea what this is, but I know there are some people who definitely know what this is. Who here knows what this is? Okay, there's some that don't. Okay, so this is an hour ago. So this is basically my childhood in a little black box. This is a game called Simon that I played a lot as a youngster, and that can possibly tell you how old I am. Let's not dwell on that, shall we? And this was well before we had fun things like Nintendos and PlayStations and Segas. We all remember Sega, don't we? And this was a memory game where it literally all it did was flash colors at you in sequences and you had to remember them. So it would start with, say, yellow, and you'd click yellow, and then it would go yellow and red. And you'd click yellow and red, and then it would go yellow, red, green, and you'd click yellow, red, green. Did I mention that we didn't have Nintendos or Segas? This is what we did for fun. And you would keep on going, like, sequence after sequence after sequence, until you literally ran out of memory and could no longer remember what the sequence was, and you would lose. And this was something I would do for hours and hours and hours on end. So, I'm here to talk to you about Simon, but I'm also here to tell you another small story. So, I have a coworker. His name is Sandeep. He's a good friend of mine. And he and I share a passion for Simon. This is a game we really like to play. And some of the new Simon versions, you can play them multiplayer. And we really like to play this game multiplayer. It's really, really, really fun. It's something we do a lot of. But we have one very small problem. We're both developer advocates, and case in point, like, we travel a lot. So we're not physically in the same place at the same time to play Simon together. And that makes us very sad. And we don't want to be sad. We want to be happy, and we want to be playing Simon. So we thought to ourselves, we're smart, right? We have the power of the internet. I'm sure we can come up with something that'll help us solve the problem. So we figured, I know what. Let's make a multiplayer Simon Says game that we can play over the internet, and then we can play Simon wherever we are as often as we like. So that's what I'm going to talk to you about this evening. We're going to go through how we ended up deciding how we were going to build this, and we're going to look at some really cool technology that enabled us to build this really, really cool stuff at scale and really quickly. So the first thing we sat down and said is we said, okay, we want to build this multiplayer game. What do we want to do? Like, what technology do we want to use to build this thing? So the first thing we thought was, okay, we need to start with communication protocol. How is this thing going to talk to like a server and back again? How is that going to work? That's where we want to start, because if we don't get this part right, then maybe we won't have a Simon game at all. And we came up with a checklist. We figured, okay, this game has to be real time, or at least close to real time as we could get. You know, I don't want to be pushing red on my end and then having to wait like 3 minutes for him to see a light show up at his end. That would be really boring. That's no fun at all. We want it to be secure, because clearly Simon is the most hacked game on the planet, right? We can't have cheaters, we can't have people hacking this game. That would be terrible. It needs to be reliable. Like, it's almost worse when a game like stops halfway through, Pokemon Go crashing. That would be terrible. So definitely has to be reliable. And we also came up with a realization that we needed it to be cross-platform. That became really, really important, because when Sandeep and I sat down to build this thing, he was like, oh, cool. I'm going to build like this IoT hacking thing with like Arduinos and electricity and things that could possibly fry you. And I went, that sounds terrifying. I don't want to do that. I'm going to build a nice software thing using Android. And I also want to build a backend server using Go. Right? So he wants to build this Arduino thing that talks to a server over these microservices. I want to build a Java thing that wants to talk to my backend services. And I also want to build my server in Go. So having a communications platform that's going to work with mobile devices, that's going to work with Node, with embedded devices, and it's basically, you know, almost any choice in language that I want to use on the backend server became very important, because the types of things we wanted to build here were very different. So we sat down and we were like, okay, what's going to fit these needs? What's the actual thing that we can use to build all this stuff in? And strangely enough, we settled on gRPC. So, hands up here people who know of gRPC. Hands up here people who have used it in production. If doing demos counts as production. So, if you haven't heard of gRPC, gRPC is a high-performance, open-source, general remote procedure call framework that puts mobile and HTTP2 first. So this is the microservices part of what it is that I'm talking about today. Google has been using a general-purpose remote procedure call framework internally called Stubby for ages and ages, and this is simply an extension of that source code, really. They connect a huge number of microservices internally. We do something ridiculous, like order of 10 to the 10 remote procedure calls per second internally using this technology. So when Sandeep and I sat down to do this, we were like, okay, well if they can do that many, I mean, it's probably going to be fine for Simon. Like, we might do a little bit more traffic, but like, that's fair enough. So we were like, okay, this gRPC thing sounds reasonably like it might be a good project. So, what does gRPC give us? So, the first thing that gRPC gives us is a technology called protocol buffers. So protocol buffers is actually technically another open source project that's used quite regularly within gRPC. It's another open source project that is a language neutral and platform neutral extensible mechanism for serializing data. What does that actually look like though? Those are nice buzzwords too. So the cool thing about protocol buffers is that you write what's called like an interface definition language. So you write this .proto file. And that basically explains the data structures and the services that you're going to have inside your application. Right? This is really cool because then protobuf can also know, hey, this is the format that data is going to go across the wire as well. And it can build those data structures internally for the binary formats on top of that as well. It's also built on top of HTTP2. This is good because fast. HTTP2 gives us a lot of really neat things that generally means it works at a much faster rate than the good old HTTP1. This is an example that you can actually go to right now if you want. The URL is at the top. And it's basically pulling down a whole slew of little itty-bitty tile images in one go. On the left, you can see the HTTP 1.1 version. On the right, you can see the HTTP2 version. Oh, that's, no, I switched that. My left, your right. But you can see the HTTP2 version works quite a bit quicker. This works this way because HTTP2 gives us a bunch of features that we can also take advantage of as well out of the box. So HTTP2 does multiplexing. This is really cool. One of the reasons why that thing is so fast is because it doesn't have to do multiple connections every time it wants to do something. It has a single TCP/IP connection to the server that it's talking to, and then it can send multiple requests backwards and forwards in a non-blocking way up and down that stream. That makes it really quick for these sort of RPC calls, as well as pretty much anything else that it's doing over HTTP2. Because we have that single TCP/IP connection, we can also do bidirectional streaming, which is also really, really cool. So we can send data up and down, we can ask for requests and responses in an asynchronous fashion. So we can do some really interesting stuff, much like what we want to do here with our game. gRPC by default works over HTTPS, so yay, security, that makes us really happy. And it also gives us flow control too. This works really well for huge numbers of microservices, especially if those microservices are being called from, say, embedded devices or mobile devices, because it gives it the ability to be able to stand there and go, whoa, you're hitting me too hard. Maybe slow down a little, please. Like, just chill out. I'll get to questions at the end, it's all right. Where was I? Cool. Finally, and we've talked a bit about this already, gRPC supports multiple languages. So if you have a problem that can't be solved with Go, Ruby, PHP, Java, C, C++, C#, Objective-C, Python, or Node.js, come talk to me later. It sounds like a really interesting problem. And it's pretty cool. Talk to me later. But the really cool thing about gRPC is it's not just like a library, but a set of tooling as well. You're able to generate this code that means that you don't have to worry about things like binary protocols, what's the format the data is going up and down, do I need to do retries, do I need to do all this sort of stuff. It gives you this really great RPC framework just right out of the box, which is really, really awesome. Cool, so we stood back and we were like, okay, this thing is real time, right? It runs pretty quickly. We can send a lot of RPC calls per second. That's pretty good. It's secure, runs over HTTPS, sweet. It's reliable, so things like flow control, so that's really nice too. And it's cross-platform, you know. My friend Sandeep can do his Node.js stuff that works with the Arduino. I can do my Java stuff that works on Android. And I can work on the back-end server, which I want to write in Go. And I can communicate across all these different platforms using this RPC microservices architecture without having to worry about data interop, you know, what format is coming into the wire or anything like that. I can work on it in a canonical way across all these languages, which is hugely, hugely powerful. Awesome. So let's have a look at some protofiles and see like actually what this thing looks like. Excuse me. So here we have the protofile that Sandeep and I came up with when we sat down and wanted to work on this project. So up the top here, you can see that, yeah. Here we've defined a service. Here we're using what's called a bidirectional streaming service. Now there's a variety of different RPC services that you can use. But for this particular game, we just need to be able to send like data up and down in essentially an asynchronous manner. So here we're able to send a stream of requests. Which way? We're sending a stream of requests from the client to the server, and then from the server we can send back a stream of responses. What does that data look like? And we'll step through this a bit more too. A request is either one of two things. Really, it is saying, hey, I'm a player and I'd like to join a game, please. Or it's saying, hey, I've pressed a color. Right? So there's my client, I pressed a color, it sends the message. Responses from the server tend to dictate game state. So, hey, I've started a turn. Hey, I've stopped my turn. You've won or you're lost. Or it's saying, hey, I'd like you to light up a color, please. And we'll look a little bit more of that later as well. So, a typical sequence within this game would look something like this. So here we have the Node.js client. It's pinging the server, and it says, hey, I've got a unique ID of 1, 2, 3, 4, 5, because that's how I roll. And I'd like to join a game. And the server says, okay, cool, I'm going to wait for a little bit because I've only got one player. And then someone who has my fantastic Java Android client does the same thing with their unique identifier of 67890. Says, I would like to join a game now too. And the server's like, oh, cool, I've got 2 players now. Excellent. So I'll send them both a response back saying, hey, we're going to begin a game. Now I need to arbitrarily pick one of those to start. So we'll pick the Node client. We'll say, hey, it's your turn. You start your game. So you want to press a color at this point. Here it is. You start. So the Node client on the IoT device then says, cool, I'm going to press yellow. And says that down the pipe. Now the way we've implemented this is we've implemented like as little smarts in the client as possible. That's not to say that you shouldn't do that. That's just saying like this is how we did it. This means that for both the devices to actually light up, there has to be a full round trip for it. This actually works quite nicely in the demo because you can kind of see the speed in which that message goes backwards and forwards. So it tells both of them, hey, light up yellow please. They show yellow. And then it tells the Node client, hey, stop your turn, because it's their first turn, we only want one color. And Android, your turn now. Now, unfortunately, the Android player is not a very good player. So he presses red, which is a lose. Now first, we tell both of them, hey, we need to light up, so that's fine. And then it says, sounds like there's something tripping behind me. Then it says, is the Node client win? And it says to the Android client, sorry, my friend, you lose. And that is basically the general gist of the game states and as they occur within this game. Cool? We're good so far? Excellent. So I'll show you some of the code, too, that powers the gRPC side of things. So you can kind of see which bits are built for you, which bits come as standard libraries, and you can see how they work. So I'll start with the Java one, mainly because it's the most complicated, and then we can work backwards from there. So here we are connecting to the gRPC server from the client. There's this thing called a managed channel builder. Really, what I'm saying here is you just need to tell it, connect to this host and port. Right? This is something that comes standard. But from the proto file itself, we get this Simon Says gRPC stub. That gets generated for us. And we can take that channel connection and pass it through. There's a few different types of stubs. There's a sync stub and an async stub, but that's the general gist. And from there, we get these things called stream observers, which basically is how we handle streaming within gRPC. Hands up here, people who have written Java. Sweet. We're all sad.
And write a lot.
It's too easy to pick on Java. I shouldn't do it. I pick on everything. It's totally non-denominational. So this async stub takes in a stream observer responses, and really the most important part of it is it's saying, okay, whenever I receive something from the server, fire this on next event, and then go do something with it. Here I'm going to receive responses. I'm not going to go too deeply into that at all. Just say that, yes, we've got something from the server, let's go do something with it. From there, I've also got a stream observers of requests as well that I end up returning. It's worth noting. This means that then I can put stuff into the onNext event for that comes back. So I can asynchronously send stuff to the server. And this all gets handled for me. I don't have to worry about, again, we're not dealing with like wire protocols, we're not doing anything. We just have these standard interfaces that we can interact with. So here, if I want to have a player join the game, I can pass it through that stream observer requests. I can build this player object that gets generated from my proto file in a very Java-y way. I can specify some unique player ID for it. And then I can just say, hey, add it to my request data structure, and pass it through to onNext. So, to repeat myself again, this is sending data to my server. I'm not doing anything in particular. I'm not converting it to JSON and sending it down the pipe. I'm not turning it into some binary format. That interrupt side of things I don't care about. It's not important. If we want to look at exactly the same thing on the JavaScript side, right? So this is a JavaScript client. This is the one that's running on the Node.js one. On the Node.js client that's running on the little Arduino board down there. It's a lot simpler because JavaScript. We can pick on JavaScript too, it's totally cool. I don't mind. So here instead, we go, okay, rather than generating code, we actually just hand it a proto file and then it builds stuff dynamically at runtime, because JavaScript. To connect, it's a much simpler statement, but we just say proto. Simon says, hey, connect to this server on this particular port. And we have this game object that gets created that we're able to use from the client. And really, we want to send events down. That's all we have to do to send a player event. Hey, let's join this game. It's a very simple little thing. And we just say write. And again, no serialization, no worries. To receive events, we have an on event, an on data. And that's all it is. We don't have to worry about when this gets called. It gets handled for us. So we receive events that come through, and then we're able to take those values out of those events. So here we have, for example, the light up event comes through. The event type is light up, and we actually light up some colors on our stuff. So that's all our, that's our client-side code. That's pretty straightforward for doing serialization and deserialization and sending a lot of data over a wire in a really tiny binary packet. That's pretty cool. On the server side, what does that look like? People here who write Go. Wow. Okay. That's actually new for me. That's good. That's fine. We should get more of you. Congratulations. That's fine. But, so this is that was good. That was surprising. I haven't had that happen before. That's fine. It's a little creepy pen. I'm like, yeah, it's me. Excellent. So we have the same thing happen here as well. So we get some generated code. Actually, this is primarily all generated. But this is the interfaces, right? So if you've written anything with interfaces, you should be able to look at this to a degree and understand. This is the interfaces that get generated from the proto file. So I have this Simon Says server. It has that RPC call we were talking about game. And I get an interface of Simon Says server that I need to implement, which is up here. So I go off, I write my implementation of what should happen when game gets called on the server. Right? And then it's up to gRPC to make sure that that thing gets called when I register it with gRPC. I don't have to do any more work than that. From there, right, it passes through this Simon Says _ game server, and now I'm really happy because not many of you write Go, because it's actually a really bad Go name. I don't know why they put an underscore in it. That's just one of the things they did. But for me here, right, if I want to send stuff to clients, right, these connected devices on this like streaming microservices, I just send a response. If I want to receive stuff, right, in any synchronous way, I just hit receive. And that's all I need to do. So for example, when we're looking at receiving that initial join request from someone who wants to connect to the game, I just say, hey, I've got this stream here of my Simon Says game server, and I just want to say, could you just receive that for me? And it'll actually block until that comes through. Go gives us really nice concurrency primitives, which I'm not going to talk about today. That's fine. But it makes that sort of stuff really, really simple. But that's, like, again, that's all I need to do. So that's kind of like the gRPC side of things, right? I wrote some really nice code, did a lot of the heavy lifting for me for this communications mechanism over the wire. I'm interacting with these objects over microservices that send streaming data, but it kind of looks like I'm just calling like procedure calls, right? It's called remote procedure call for a reason. And that's good. So, great. We now have this great microservices architecture. And because it's called a microservices architecture, it will be perfect. Because that's the best buzzword of today's day. But we have one very small problem. This game's going to be huge. I mean, once people realize they can play Simon multiplayer over the internet, like this is going to be crazy. Like everyone's going to want to do this. So we can't just be like, oh, you know, let's just chuck it in a server under the desk, right? When I wrote this, this backend service, I'm actually using Redis for some persistent data as well. So I can't just be like, oh, let's just have a server under the desk that has Go on it, and another server under a desk that has Redis on it. That'll be fine. Yeah, what's the worst that can happen, right? We don't want to really do that, right? So if we're really planning for scale, that doesn't sound so good. We want something that's actually truly elastic and in the cloud. That would be really great. And maybe does some more stuff for us. Like, I don't know, maybe just make sure that, you know, if stuff is not up anymore, it resets it. Or handles things like deployments. Like, how do I update this thing on a regular basis? Am I SSHing into a server every day? I don't want to do that. That sounds hard. So what can we get that does that sort of thing? And it means that when people actually realize how amazing this game is, we can handle like massive amounts of scale. So this is where I start talking about Kubernetes. So any Kubernetes users here? Whoa, yay! More than the Go users, that's fine. It runs on Go, so that's okay, that's fine. So, if you haven't heard about Kubernetes, all right, any like Docker containers?
Just a question between the gRPC. Does it support also some more standard servers and writing something in Go?
It supports all 10 of those languages I mentioned.
Can you repeat the question?
So the question was, does it support any other languages?
Not languages, application servers.
You don't need an application server with it. I mean, you can stick it behind any sort of TCP proxy if you want, like a network load balancer or something like that. But it comes with an inbuilt server. So the application server is kind of like, you're not serving static images through this, you know, you're not serving it through anything else. So it starts up on a port and you're just good to go. Go back. Go on. Well, I know you had a question waiting and you're just dying.
How is that like comparing to other framework that we already have in the system, like Socket.io, Atmosphere for Java, and I don't know, Thrift.
So Thrift is probably more comparable. Thrift is more comparable, and it's funny because we go back to conversations about how Google used to open source stuff and how it does now. When you look at things like Thrift and whatnot, that's kind of, I see that coming out as how Google used to open source stuff, which was, hey, let's write a paper, and if you want to do stuff with it, that's yours. There you go. And people go, that looks really, really cool, so we're going to build Thrift, and there's some other ones as well that I can think of. Whereas now we're more like, no, let's actually build this thing for real and build a community around it and actually like turn it into a real product. And that's where gRPC really sits. There's nothing necessarily wrong with Thrift in any way, shape, or form. I think it's I've never used it, so take that with a grain of salt. I think it's a little tricky to use, from what I've heard. I think gRPC and the process for gRPC is a lot nicer. Also, I think the HTTP2 benefits are really, really huge for using gRPC. Did that answer your question?
Almost.
Fair enough. So, in terms of your question, in terms of Socket.io, the big difference here is right now you can't use gRPC on the browser. Yet.
But why would you want to? Because the protocol is binary, so it's not
So,
readable.
if your client isn't one of these, or is this plus a website, it would be nice to be able to go browser and this without having to put like a WebSocket in between to proxy the traffic. That would be handy. And then you can still do streaming, like you could do streaming RPC calls, which is great. Or basically, in the same way you treat REST now, which can be accessed from anything, you'd be able to treat gRPC.
Does it only works in podcast? Like when the server sends all the clients receive?
So no, it's a connection. So it's an RPC call. So I call the server and say, hey, like let's talk. And then they talk to each other. And then it's up to you to send out whatever you want to whomever is connected to whatever's connected on that. I can do RPC calls like, hey, like a standard method response, right? I call your thing and you give me a return and we're done. I can send a thing and be like, hey, let me do a thing. And you'll be like, let me stream you a bunch of data. Or I'll be like, hey, let me stream you a bunch of data. And then finally you're like, no, let me send you a single response. Or we can do what we're doing here, where it's, hey, let me stream you a bunch of data. And it's like, hey, I'm going to stream you a bunch of data back too. And we'll be done when we're done. That's fine. So there's a variety of ways you can do this. Go for it.
What about the threading model?
What about, sorry?
The threading model. Is it only a callbacks that I need to use as soon as possible, or I can use the gRPC threads to do my business logic and all the processing on it?
All the threading models pretty much use whatever is native for that language. So for Go, it uses, well, it doesn't use anything actually, it's up to you. It blocks and it says if you want to use like basically channels and Go routines, you can. Java, it just uses, you know, it just builds its own async calls into it, so it just uses callbacks. What are the other ones? It's basically all of it's canonical up to the actual language. That was asking about the threading models. Sweet. Good. All right, now I can make more silly jokes about Kubernetes. So, Kubernetes. Let me get my train of thought back. Perfect. So, open source container orchestration from Google. Container orchestration system from Google. This is a really, really cool project, one that gets me really, really excited. Who here has heard of, like, when we talk about, who's here has heard people talk about Borg inside Google? Not as many as I thought. So, okay, that's fine. So, Google's been running containers in production for years and years and years and years. And they've done that on a system called Borg. Up until a point, we really didn't talk about it very much. Kubernetes itself is actually a greenfield, brand new open source system that was built with all the lessons we learned running containers at ridiculous scale. And basically, we're giving it to you for free. What makes it really, really cool is not only can it be like, hey, I want to run 100 of these containers or 100 of these applications, but it also gives you these standard tools for saying like, oh, well, if it's in a container, right, so it's abstracted, that's great, sweet. But here's standard ways of doing health checking. Here's standard ways of doing deployment. Hey, here's standard ways of pushing stuff out behind a load balancer so it doesn't fall over when like things go wrong. Or if things go right, let's just make sure there's no downtime. Let's solve all these really standard problems that we all have with just building and deploying and just managing software systems. And let's just do it easily and give it to you so that you can use it. And that's hugely, hugely powerful. And I think one of the biggest things about containers, and one of the most exciting things I think containers can give us, is really that abstraction that allows us to get very generic solutions to very common software development problems. And that's really, really cool. So, with Kubernetes, suddenly we're like, okay, deployment problems, we know how to do that with Kubernetes. It's very standard. We'll look at that a little bit later. Scaling problems, we can run clusters of machines inside a cluster for Kubernetes. So we can run things at scale. And the other cool thing is Kubernetes does is, again, solves a very simple problem. If one of these applications goes down because memory leak or something's bad in the code, just resets it. Starts it back up again. So it keeps things alive for us as well. All standard sort of problems we've all had as software engineers. So rather than looking at things like this and saying, oh, let's actually, like, we have virtual or physical infrastructure where I'm like, this Go server goes on this particular box, and this Redis, instance goes on this particular box. Instead, I just start thinking about my application on the whole thing in terms of like layers. I think of it and I go, okay, I've got a bunch of machines, but on those machines, I want to run 10 instances of my Go server. And I want to run, a nice little 4 cluster of instances of this Redis application. And suddenly the actual infrastructure starts to disappear. And what I really think about is my application. So let's talk about some of the fun things that Kubernetes does and how it does it so that we get to this wonderful utopia of software development. And we can be a little less hand-wavy. So before we look at some actual code about how this works, I'll talk about 2 concepts that I think really kind of explain how Kubernetes sort of works behind the scenes. So the first concept is an idea called cattle, not pets. I keep asking you questions, but who's heard this term before? A few of you. Not all of you. All right, about the same number of people as done Kubernetes work, strangely enough. So this is an analogy that I am going to apologize for up front, especially those of you that are vegetarians. It is a horrible, horrible analogy, but unfortunately it explains things really, really well. So, what is a pet? A pet is something that has a name, right? It's unique and it's rare. I have a wonderful dog. Her name is Suki, right? If she gets ill, I take her to the vet. Anything happens to her, I take care of her. Everything is wonderful for her. She is just so spoiled, it's ridiculous. But in the world of the cloud, we really don't want pets, right? If we want to be truly elastic and truly scale, what we want is we want cattle. We want one to be much like the other, right? We want them to run as a group and we want to interact with them as a group. And yes, if one of them gets ill, we make some hamburgers and we just get ourselves a new cow. I warned you, it's a terrible analogy, but it does explain things really, really well. So, we want cattle, we don't want pets, right? We want cattle. The other thing we want to do is an interesting sort of shift in developing software, I think, which is we want to think about it in terms of desired state. What do we actually want from this application? What do we want to have running? And we want our systems to basically just take care of that for us. We don't want to be doing that manually. We don't want to be doing it to ourselves. So when I get into a car, I want to get into a self-driving car. I want to tell it my desired state. Take me home. I honestly don't care about how it gets me there as long as it's reasonably quick and does a decent job of it. Instead, I don't want to be getting into another car and being like, okay, let's turn the key in the ignition, great, now let's put the clutch down, sweet, and let's go into first, and then put my foot on the accelerator while I'm lifting my foot on the clutch. Whoop, going too fast, okay, let's brake a little. Now let's go into second by putting the clutch down again, okay, don't grind the gears. Like, I don't want to do that. Like, yeah, sometimes it's fun to drive for fun, but I don't want to be doing that all the time. I have more important things to do, like play Pokemon Go. Way more important. I don't know, like,
There's a gym here.
yeah, there's a gym in this building and no one told me. So, putting those concepts together, you know, this is the ideal solution, right? We want to have copies of these that can die at any point in time, and we want to tell our system this is what we want and have it manage it for us. So what does that look like in reality? Let's actually dig into what sort of Kubernetes does behind the scenes. So for starters, Kubernetes basically treats the number of machines we have as a single entity, right? So this is probably what our thing really looks like if we actually look at our infrastructure. We have multiple copies of our Go program running, a couple of copies of our Redis program running, and then when Kubernetes comes into the mix, it treats it all pretty much as a single unit. Right? This is a single unit of resources that is available to it. This means that if one of them goes down because memory leak or something similar, oh, it came back up already, then it could come up in a completely different machine. And the great thing is, we have cattle. That's okay. And we trust our systems, so that's okay too. That's wonderful. This also means that if an entire server actually catches on fire, as long as we have resources available within that cluster, all of that stuff will automatically get moved over to somewhere else. And that 3 o'clock in the morning phone call that we all dread can probably get dealt with at 9 o'clock in the morning, assuming the fire department gets there in time to put the server out before it sets other ones on fire. That would be bad. So, how does Kubernetes do this sort of thing? And I like to explain this a lot because I feel like if you can understand the basic idea of this loop, then you actually understand at a core level what Kubernetes really does. So, for example, there's a thing inside Kubernetes called replica sets, or if you use older versions, they call it replica controllers. You can flip those two words in your mind as much as possible. But this is where we actually say, hey, we want, say, 10 copies of this container of this application running. And we build this thing called a replica set. And it goes into this control loop where it says, okay, how many of these things am I meant to have? Because you've told me. Oh, I need 10. Okay. How many of these do I actually have? I have 0. Okay, let's diff the 2. All right, I need to make 10, and then let's act upon it. All right, let's create them. And then I come back around again and I say, okay, how many of these am I meant to have? 10. How many do I actually have? 10. All right, do I have to do anything? No. Fine. And then maybe, I don't know, 1 week, 1 day later, it comes back around and it says, how many of these am I meant to have? I have 10. Oh, I have 9 now instead, actually. Oh, okay, well, let's diff that. We need another one. Let's bring that back up. And so you can get this loop happening inside the system where it just keeps checking. Hey, is this the way it should be? If it's not, let's make it so. And if you can understand this loop, you can understand things like this is how auto-scaling works. This is how deployments work. This is how a lot of Kubernetes works behind the scenes. And it's really, really, really powerful. All right, let's look at some actual code that runs and, actually deploys things to Kubernetes. So this is a YAML file. So interacting with Kubernetes, there's a variety of ways in which you can do it. You can send a JSON, there are APIs, there's a command line client, there is even a UI that's not half bad. But this is really like the way you will probably end up dealing with it more often than not. Sending it YAML files, because writing JSON by hand is awful, don't do it. And it's pretty straightforward, right? So I'm going to send this thing. We can ignore the fact it says deployment for now, because I just don't want to talk about it. We don't have time. We tell it, hey, we want 10 of these containers to run, please. Which containers would you like me to run? I would like you to run the Simon Says server containers, please. GCR.io is the private container registry that comes with a Google Cloud Platform project, so you can just ignore that. So it runs those, great, and I'm going to get you to set some environment variables when those containers come up. So here is Redis. I've already set that up elsewhere as a DNS record for it. We'll talk about that later. And point it here. And while you're at it, can you just expose port 5051, because that's the standard gRPC default port. And then I'm able to hand this over to Kubernetes, and Kubernetes will make sure there are 10 of these containers running with all of those values. That's it. Okay. That's pretty cool. Now there is one other thing I want to point out here that we will talk about later, which is this little metadata section hiding over on my left. It's a little sneaky. Basically, this is just a nice way of applying arbitrary key value pairs to any container that is running in this set. And we'll look a little bit more there. So that means that all these Simon Says server containers have a role, quote unquote, of Simon Says server. And these are values that I picked out, right? They're relevant and logical for my application. So cool. That means that now I have 10 of these running on a server, much like this. But we have a problem, right? It's great that we have 10 of these running on a server, but where are they running? How do we access them? You told me they were ephemeral. They could go down at any time. I don't have an IP address. What do we do? Help! So we have a wonderful thing that gives us a static IP and a concrete way of being able to access these things. And if you're thinking to yourself, a load balancer would be really handy, you're pretty much exactly on the right money for exactly what we end up doing. So Kubernetes has this concept called services, which are essentially a load balancer that sits in front of these containers, but intelligently knows where they are, so you don't have to do any of the work, and exposes them either internally to inside Kubernetes or externally to the outside world, or both, really. The way it does that, which is really cool, is it has this thing called a selector. Right? Remember those labels we were talking about just briefly before? The way we expose things is we say, I want you to expose all the things that have these particular labels. So you get a really nice decoupling from what it is that gets your pods up and running to the other thing that actually exposes them. This is really, really powerful. So here is the YAML, strangely enough, of what we end up doing to expose a service. You'll notice it's called a service. Here is our selector, right? So we want everything that says role, Simon Says server, which is what we had previously. That's great. Now, we don't actually have to expose this to the outside world. As I said, if I didn't add this line at the bottom, it would just be inside Kubernetes. But in this particular case, yes, I do, because it's the game that I'm going to demo amongst all of you. So I add type load balancer, and on Google Cloud Platform, that actually creates a network load balancer, which is great. And so it is now exposed to the outside world. It does similar things on other cloud providers, and you have other stuff if you want to do it on-prem as well, which is also very good. Okay, so you now are experts in Kubernetes. Wonderful. Let's make a demo happen. Sound good? Wonderful. So what I am going to do now in front of your very eyes is build the infrastructure for the game that I was talking about, and then we're going to play it. Does that sound good? So let's throw that up there. So, is that readable from the back? Excellent. So here I have a little visualization up the top. I'm actually going to drop this down just a tad. That's actually the 3 nodes in my cluster. We're not going to talk about those too much. But we'll be able to see sort of, we'll be able to see containers as they come up. So I've got some make files to make this easy, because typing in front of an audience is hard, and I try and keep the typos to a minimum. So if I want to create, no, what was it? Redis, thank you. So I'm going to create basically all the clusters, all the Redis machines. So it's just the one. I'm actually just going to create this one container for Redis. I'm not going to talk about how to make that data persistent or anything like that, because I'm too much time. But for just simplicity's sake, here's my Redis instance. Right? I need to expose that to the outside world, so that's my container. I need a service. Let's put that back up to the top so it's a little bit easier. So here you can see me setting this YAML file up like I did before. kubectl create, I tell it -f, here is my file, and it goes on up, and then it creates that service for me. Right? And that was pretty quick. This isn't creating a load balancer, so that actually comes up really quickly. So now I have Redis available to me inside my cluster. The cool thing is, you noticed before that we had Redis as a DNS. There's a nice add-on that comes standard with GKE, and pretty much everyone uses it. So if I have a service named Redis, it's available on the DNS Redis. Makes sense, right? So cool. All right, so we have Redis available. Now we want to have that Go server and have it connect. So let's create that. I want to say server rs. Yes.
Those are the physical servers?
So this is a cluster I have already created. And I have a cluster of 3 machines. And these containers are all getting created on this machine. So here I have 5 of those Go servers running. Great. So I can connect to it with my devices I have here sitting on my desk. I need a service in front of that. Those are talking to Redis. So make, where are we? Create, no. Server service. So here we're going to have a service that sits in front of that. Again, this is all kubectl command lines, right? Nothing special. So here that's creating a service. Now right now what it's actually doing is creating a load balancer. This takes a minute or 2. So I need to distract you with something fun. So why don't I do that? So here we can see we have 5 of those instances of that Go server. But if you remember from our original example, we had 10. So let's make it 10. Where are we? Resubs? How did I do this? Now I forgot my own command. Oops. Bear with me. Thank you. This is fun to do with, that's better. Oh, I run weird stuff, don't mind me. There it is, server resize. There we go. Let's tell it to make 10. It's all right. I landed here at 5:30 this morning. You've got to give me some leeway. Excellent. So now I have 10 of those. That was that easy. That was how easy it was for me to say, hey, let's make that 10. If I wanted to, I could set that up to do auto scaling and do a whole bunch of other stuff. But I think 10 instances is at least enough to handle the initial load of my game Simon Says server. So now I have an IP address. Excellent. That's great. Now I can play this game. So let me get this connected. What's the easiest way for me to do this? So here's my devices here on the left here. I have my IoT box, which is great. And then on the right here, I have my Android client. So I'm just going to grab my IP address. And we will paste that in. So assuming everything goes well, this should now flash up pretty lights. Welcome to Simon Says. Excellent. Okay, and then if I take the IP address and I plug it in to here, 104.197.156.189. Just double check that, because if I type it wrong, bad things happen. This looks right, so I'll connect it. Excellent, we're all flashing. Welcome to Simon Says. Okay, so the 2 devices are now connected and they've been match made. Perfect. Can I have a volunteer from the audience? Who wants to play Simon Says with me? Please, come on up. Excellent. Please, you can come on this side, because you want to play on this box, because it's the fun box. I've totally forgotten whose turn it is. It is your turn. So, pick a color.
Don't look.
Alright, so I got red. Okay, so you'll notice that here it's red, right? It flashed, the message went straight to the server. This actual server is actually in the US right now too. Alright, cool, so red flashes on both. I'll go green next.
I'm going to do red, green.
Red, green, and then you add another color. I give you fair warning, I've played this game a lot. Red, green, red. Oh, I have not played this game a lot. Okay, well, that was... I came in at 5:30 this morning. Wonderful. Okay, so, in conclusion, we've gone from having, like, a non-multiplayer game, which is incredibly boring, to this wonderful multiplayer game that uses gRPC to do, like, really fast, secure, reliable RPC communications in, like, a streaming manner that is really nicely abstracted away. We didn't have to do a lot of heavy lifting to get it. We just had to use these really nice tools to allow us to do this sort of communication, which is really cool. On top of that, we're able to build this thing so that we can handle practically, well, I don't want to say any scale, but any scale. Right? We're able to leverage the abstraction that containers gives us over software, which is hugely powerful, and then take Kubernetes, which is a great orchestration container system, to allow it to, allow us to resize how many containers we want, allow us to deploy really easily, allow us to make sure these things stay up and stay healthy, which is great. And this now means that wherever Simon, Sandeep, and I are, anywhere in the world, we can play Simon Says as much as we like, which I think is really, really cool. So before we wrap up, and let me go to the next slide. No. Give me the mouse back. So before we wrap up, some resources and some thanks. Obviously, I'd like to really thank Sandeep. He and I worked on this together. It was a great fun project for us to work on. Loads and loads and loads of fun. Also, I'd like to thank one of my teammates, Jen Tong. She built the little plastic box. I know nothing about hardware. That stuff terrifies me. She is amazing. She made a bunch of it for us. And if you're interested in, well, pretty much anything, actually, she's a great person to follow. If you want to learn more about this stuff, gRPC.io, Kubernetes.io, I've got a bunch of resources on both. If you're looking for something real-time, gRPC actually has a Gitter. Like you can go on GitHub and chat with people about it. Kubernetes has a great Slack channel as well. If you want to get started with Kubernetes, and I say this from a seemingly biased perspective, but in a lot of ways it isn't, I would say get started on Google Container Engine. Like just sign up for a free trial, give it a go. The reason I say that is because it totally removes the pain of setting up a Kubernetes cluster, which right now is a small pain point for us, and is getting better, thankfully. But you can walk in and say, hey, I want a 3-node cluster, I type 3 here, I push a button, boom, I have a cluster. And it means you can actually get going with it and try it without worrying about hitting any gotchas around actually setting up a cluster, which is really cool. And then if you decide, hey, maybe this isn't the right fit for you in terms of where it's running, that's totally cool. I respect that. And one of the power of Kubernetes, which is great. Finally, as I mentioned before, I'm one half of the Google Cloud Platform podcast. We've had episodes on gRPC. We've got, actually I think we have 4 now on Kubernetes at least. And we mention on a regular basis. If we don't have 4 now, we will have 4 in the coming weeks because I just edited one on Kubernetes, or at least 2. So podcasts are your thing, and you think I'm at least mildly entertaining. I'm at least half as mildly entertaining on the podcast because there's 2 of us. That math sort of checks out. That's fine. And before I finally get to questions, thank you so much for having me and sitting here and listening to me. I really appreciate it. I hope you got something valuable out of it and you learned cool things. So thank you very much. And I'm sure you have a question sitting in the front.
Let's say you have 2 microservices, type of microservices, that both of them are CPU intense.
Okay.
And you want to ensure both of them will not run at the same physical.
So the question was, if you have 2 microservices that are, say, very CPU intensive, how do you basically tell the scheduler that this is what they're like, so that it can appropriately place them in the cluster? So I don't show that here, but there is resource constraints that you can add into that YAML file around memory and CPU. So you can be like, hey, this is how much CPU this thing needs, or this is how much memory this thing needs. And so the scheduler can look at how much resources it has in the cluster and say, well, we shouldn't put these 2 things together or allow them to have too little resources on a single machine if that's not what's available. And then it can distribute the load as necessary across that whole thing. But yes, there's totally that stuff in there. There's so much stuff inside Kubernetes that I didn't even touch on, so feel free to ask more questions. I'm going to go to the back row. I feel like I've been aiming mostly at the front. Go, far back. Yeah.
Two questions, please. First, you mentioned Borg.
I mentioned what, sorry?
Borg.
Borg, yes.
Yeah, so Kubernetes is the new Borg, it's the Omega project? Or it's run on top of Borg?
I can't speak to what we run inside Google.
Okay.
That is my answer.
Okay. And another question, if I compare this, I don't know if it's really comparable, but if I compare this framework to Mesos, or
Yep.
Yarn, something like this, it's come to solve similar problem, or it's another framework with
Solving, I think in the end of the day, when people use those frameworks, you end up, I don't know so much about Yarn, mainly because I don't know anything about Yarn, really, at all. Coming to, like, Mesos is very cool. I think the big difference is the Kubernetes comes batteries included, right? So the question is comparing Mesos to Yarn and to Kubernetes. So yeah, Kubernetes comes batteries included, right? So we have logging aggregation, health checking, like deployment, like that's all like here's Kubernetes. Mesos is like, which scheduler do you want? You can pick one of 4. And that's not a bad thing, you know, that's just the way Mesos is, like the opinions of Mesos. And then it just becomes a question of, do you want something that's batteries included, and does that fit your needs and work for what you want? Or do you want to have something where you're like, let me switch out how I do my logging aggregation, let me switch out how I do my scheduling. You can run Kubernetes on top of Mesos if you want, because it's a nice scheduler for Mesos. Or you can run Marathon. So there are options. It really depends on what it is that you want to be building and how you want to build it. Next. Go for it.
Hi. gRPC
Yep.
question. Is there anything built into gRPC that allows for fallback circuit breakers, retry mechanisms, kind of historics?
Yeah, so yeah, gRPC actually comes pre-baked with, so the question was, does it come with anything like fallbacks, retry mechanisms, things like that? It comes pre-baked with retry mechanisms and that sort of stuff in the library itself, specifically for those sort of situations. So if something's kind of dropped out and you want it to be able to retry automatically, it comes pre-baked into the library and you can take advantage of that, which is super handy.
Can you use gRPC to make, I know it's not the best implement, but to make the clusters, the containers talk to each other?
Can you use gRPC to make the containers talk to each other? If the containers can find each other, which they can, yeah. It's just a TCP/IP connection, really. So as long as they know the internal IPs to each other, yeah, totally can do it.
Kubernetes doesn't come with a single pod failure, because if it's orchestrate all your pods, and if they're probably Kubernetes itself, then you're losing your own infrastructure and all your servers are down, no?
So if you have 15 servers and all your servers go down, then you're still...
No, but if you have only one engine that supports everything, so do you have any clustering in the Kubernetes itself?
So right now, okay, so do we have any clustering in the Kubernetes itself? So right now, yeah, we are still single master within Kubernetes. One of the things within GKE is we take care of that for you, so container engine. The nice thing is if the master actually goes down, really all that happens is that if something dies, it doesn't get restarted. So as long as you've got monitoring around that master, you're okay. Pushing all the way back.
How do you handle versioning of files and servers?
For gRPC? So that's a fun question. So the question is, how do you handle versioning? If we go back to somewhere around here. There we go. So the question is, how do you handle versioning? So you can see here how we have these numbers next to things. That actually dictates its position. So say you stop using like one of these, you can actually say, oh, we'll add an extra property out of 5, and things will still keep working with the old version because the number 4 tells the position of it. So you can add extra properties and do stuff like that. You can also, do red-black deployments or red-green deployments inside Kubernetes if you want. But you can keep building on this protobuf as long as you don't overwrite old properties with that numeric identifier that it has.
Just protocol buff and best practices.
Yeah.
What about if you wanted to deprecate a service?
If you want to deprecate a whole service, tell everyone, hey, we're deprecating the service and build a new RPC.
So there's no handshake or versioning?
Not that I'm aware of at this stage. We're still coming close to 1.0. I actually asked that question a little while ago where I was like, is there a way where I can say, hey, does this thing have the same protobuf definition as this thing at this time? As far as I'm aware right now, that sort of thing doesn't exist. You can bake it in. I mean, it wouldn't be hard. You just expose the version number on RPC call and see what's going on.
Does gRPC have an asynchronous client for Java or Scala?
Yeah, so what I was showing there, in my actual code, that's all asynchronous. Works perfectly. You're in the front.
It's more of the Kubernetes question. When I go outside with the services, let's say you have the Go servers,
Okay.
IP-wise, do I go outside via the service IP, or each one of the containers in the pod gets its own IP address?
So a question of like exposure. So if you want to be able to hit one of those pods from outside of the Kubernetes cluster.
I want to go outside from the cluster and try to
access
other services.
So like you're calling an external REST
Yeah,
API, you can do
exactly.
that from within the container, like any of those pods. So when I say pods, I didn't actually say that word because it gets confusing. So pods equals containers for now. So any container can access outside services. So one of the tenements of Kubernetes is that you shouldn't have to really change your application to fit inside the model of running this thing. So anything you pretty much were doing inside your app, you continue to do. It doesn't know it's inside Kubernetes. So if you want to access an outside resources via like HTTP, you can access an outside resource. Like you're just running on a server.
But let's say I have a specific IP address for each container, because let's say security-wise, I want to allow access to a certain amount of...
oh, you're talking about doing whitelisting of IP addresses?
Yeah.
Yeah, don't do that.
I don't intend to do that, but sometimes I want to be recognized as a certain IP address.
Do set ping and other security stuff that's a bit better. Yeah, I know people do that and it happens and that's fine. And I'm not a security expert, so please also take that with a grain of salt, totally. But this is, like, if you want to be elastic, you can't have, like, whitelisting of IP addresses.
Yeah, static.
You can't. So run a proxy if you have to do that, like run stuff through it, or look for other ways of use actual OAuth and good things like that. Go for it.
If I want to install a Kubernetes in my lab,
Yep.
not use the Google Cloud,
Yep.
does it add some integration with the F5, with stuff that DNS servers that running on lab, so it can communicate with other infrastructure in the lab, or just built in for defined set of computers that can...
I'm trying to understand what you mean.
For example, F5 give me a V, okay?
What is 5, sorry?
F5.
Oh, okay.
Some kind of...
Right. Oh, okay, I'm
so
with you.
it give me a V, okay? Kubernetes also give me V. So, is it replacement?
Oh, okay, so if
Is it
you're...
integrated?
Okay,
Can I
I'm
use
with
the
you,
same
I'm with you.
infrastructure?
So generally, okay, so there's a small nuance here. So if I'm running on-prem, like you say you're running in your lab, generally you don't go type equals load balancer because it's not actually going to give you a load balancer. What you actually do is you do it a slightly different way. You expose what's called a node port, and basically what it says there is it says, hey, on all the machines that are running on this particular port, I want to expose all the pods for this. That means then you can just put your regular old load balancer on the front, point them towards those ports on those machines, and you're good to go. And then that's easy. Yeah, so if you're doing that on-prem, that's exactly. So basically when you go load balancer equals true on, or type equals load balancer on like a cloud provider, they do some magic behind the scenes to avoid having to do node ports because it gets a bit more complicated. But if you're doing it on-prem, that's just the way to do it. And then it becomes very, very simple. Does that make sense? Sweet. Down the middle.
How your roadmap is affected by Docker 112 with the Swarm mode?
We're still building. So the question is, how is our roadmap affected by Docker Swarm? We just keep building cool stuff.
But many of the features of Kubernetes are no longer needed with Swarm mode.
Have you used Swarm yet? Have you used Swarm yet?
We are starting.
You're starting? You enjoying it?
Yes.
Good. That is good for you. Wonderful. We're recording, so we can have that conversation. That is actually not to make disparaging quotes about Docker Swarm. Docker Swarm is a great project. They're great people. I love them dearly. They're trying to come at things in some slightly different ways. We're trying to come at some things in some other slightly different ways. Look, if you want to say any particular comparison that I can make that is reasonable, is we've been around a little longer, so we're probably a little bit more baked and a bit more features and a bit more bulletproof. Just because we've been under testing more. But if it's working for you, awesome. That makes me happy. You're using containers. That's good. Awesome.
Thank you very much.
Thank you very much for having me.